Hello everyone and welcome to the coronavirus edition of the 13th exercise from our signal theory class. In this exercise we will practice modulations. We will start with the amplitude modulation and I will show you how to create it and demodulate it in Matlab. First we will generate our modulating signal. This is the sampling frequency. We will generate a signal that is 1000 samples long, and this is the time vector for our signal. On this line, I will generate my modulating signal. I will use a chirp signal, that is essentially a sine wave, the frequency of which is increasing over time. Remember, we used the chirp signal somewhere in exercise 4 to test the frequency characteristic of our filters. This function will generate the chirp signal for this time vector, and the frequency of the chirp signal will start at 1 kHz and it will finish at 19 kHz. Our chirp signal, that is our modulating signal, will actually look like this. And this we will use as an example of that low frequency signal that we want to use for the modulation, which will shift this signal from low frequency to some high frequency, and then that high frequency signal can be, for example, wirelessly transmitted. Now, how do we do that modulation? We will start with the amplitude modulation. First, we will generate our carrier signal. The carrier signal will be just a sine, or it can be a cosine, at the carrier frequency, and we will set that carrier frequency to be 100 kHz. Now we will proceed to implement the amplitude modulation using the formula that I gave you during the lecture. First we will take the modulating signal, that is our chirp signal, and multiply it by the modulation depth, which I have set here to 0.5. Then we will add this one, and with this entire expression we will multiply the carrier signal. Now, when the modulating signal gets bigger or smaller, the amplitude of the carrier signal will follow the suit. And that's it. In the variable y, I will have the amplitude modulated signal. So now let's plot the signals that we have generated. First, I create and format the plot of the modulating signal, that is this chirp signal that I have already talked about. Then I do the same for the carrier signal, and that is what you can see here. That is some high frequency sine wave, this signal. And last, I will plot my modulated signal, and that is what I have in this plot. And in this plot you can very nicely see how the immediate amplitude of my amplitude modulated signal is controlled by this modulating signal. Okay, now that we have created the amplitude modulated signal, let's proceed with the demodulation. I will show you two variants of the demodulation. The first will be very simple, based on the rectification and low-pass filtering, and the second will be based on the analytic signal. In this first technique, we will first rectify the signal. In Matlab, we can take the absolute value, and in hardware, we could do it using a diode. To give you an idea what this rectified signal looks like, I have plotted it here, and you can see it here in blue. Also, you can see that this blue rectified signal is just a train of pulses, the amplitude of which follows the modulating signal. Now, to remove these pulses and to keep only some local average to this blue rectified signal, we will apply a low-pass filter. Here I have the coefficients of a very simple low-pass filter. This is a very simple integrator, and using this function filter I will apply it to our rectified signal. The result will be the demodulated signal. To visualize this demodulated signal, I used this command plot, and you can see the demodulated signal here plotted in red. The red demodulated signal follows the modulating signal with some deviations. Firstly, here this transient is the time where the filter still adjusts to the incoming signal, and only here it starts to track it. Also, you can see that there is some delay between the amplitude of these pulses and the filtered signal. That is just the delay introduced by the filter. The filter cannot work in zero time. But other than these deviations, this red demodulated signal quite nicely follows our modulating signal. Now the demodulation using the analytic signal. In this approach we will first compute the analytic signal using the function Hilbert. And then we will just compute the absolute value of our analytic signal. That will give us our demodulated signal. This demodulated signal I have plotted here, and you can see it in this plot in magenta. Also, you can see that the magenta line very nicely follows the immediate amplitude of the rectified signal, which is the same as the immediate amplitude of our amplitude modulated signal. If I took this magenta signal, I would subtract 1 and divide it by the modulation depth, I would actually get something which is very close to the modulating signal. Now let's take a look what this amplitude modulation looks like in the spectral domain. With this command, I will plot the absolute value of the spectrum of my modulating signal. On the horizontal axis, I will plot the vector of frequencies which I have generated here. The spectrum of the modulating signal looks like this. This is the spectrum of this chirp signal. Here, I plot the absolute value of the spectrum of the carrier. What I get is this. This is the spectrum of this carrier signal. You can see that it is essentially just the spectrum of a sine or a cosine. Last, here I plot the absolute value of the spectrum of the modulated signal. When I plot this, I get this. And here you can see that the spectrum of the modulated signal contains the spectrum of the carrier. That is this spike and this spike. And also this spectrum was frequency shifted here, and what you cannot see, the symmetric part of this spectrum, which would be plotted here, was shifted here. So the spectrum of the modulated signal consists of the spectrum of the carrier and the spectrum of the modulating signal. So this is how you perform the amplitude modulation and the amplitude demodulation. Perhaps one more thing to note is that this rectification-based approach to the amplitude demodulation can actually be implemented in real time. As the samples of the modulated signal arrive, you can immediately apply this absolute value to each new sample, and the rectified sample can be immediately fed to this filter, from which you can immediately read the output. That is in contrast with this approach where Matlab is actually computing the analytic signal in the spectral domain using the Fourier transform, so it first needs to collect the modulated signal and only then it can compute the analytic signal. In this example, we will take a look at the frequency modulation. We will start with the same code as in the previous example where we will generate our modulating signal, this chirp signal. Here we will proceed with the frequency modulation. First we will do the modulation itself and then we will demodulate. So to do the modulation, we will first set our carrier frequency and the modulation depth. Then we need to compute the phase of our carrier. From the lecture, the phase of the carrier is given as the integral function of the frequency, and our frequency will be given as the frequency of the carrier plus the modulation depth times the modulating signal. In Matlab, where we deal with discrete signals, we cannot do this continuous time integration, so instead we will need to approximate with a summation. Instead of the integral, I will have the sum, and I will be summing the discrete signal. To properly approximate this integration with this summation, I also need to multiply each summand with the sampling period. If you do not understand why this multiplication is necessary, I will explain here. So if we want to compute the integral of a continuous time function, that means that we want to find out what is the area under that function. Now, if our function is sampled at discrete times, we cannot get this area exactly, but we can approximate it. The easiest way to do the approximation is to create these rectangles that have the height equal to the sample of the signal and the width equal to the sampling period. When I sum up the area of these rectangles, I will get an approximate estimate of the area under this curve. Now the area of one rectangle is given as the value of this sample times the sampling period, and that is what I am summing up here. So this sum is the sum of the area of these rectangles, and that approximates this integral. Also note that I can replace the multiplication with the sampling period by the division with the sampling frequency. Now in this sum I keep accumulating these values that I can also write in this form. To get the phase at time n, I will get the value of the phase at the previous time, and to that I will add the value of this summand at time n. This I will repeat, and that will accumulate the values of these summands in my phase. Note that this formula actually corresponds to a very simple IIR filter with this schematic. It is a very simple integrator. So when I want to approximate this formula in Matlab, I can do it with this filter. And that is what I have here. These are the coefficients of this filter, and this is this input of my filter. Now that I have my phase, I can just stuff it into a cosine, and that will give me my modulated signal. In this code, I'm plotting my modulating and modulated signal. The modulating signal is here, and this is the modulated signal. You can nicely see that when the modulating signal is high, the frequency of the modulated signal is also high, and when the modulating signal is low, the frequency of the modulated signal is also low. Here I would point out that the frequency change is really exaggerated so that you can see it. Typically the modulation depth is much smaller than is the carrier frequency, so the frequency changes can be much less apparent. Now let's take a look at the demodulation. Here I will do it using the analytic signal. First I will obtain the analytic signal using the function Hilbert, and then I will frequency shift it by the amount given by the carrier frequency. Next, I will obtain the phase of the analytic signal and unwrap it. Once I have the phase, I will have to take its derivative and divide it by the modulation depth. That will give me the immediate frequency of the signal, which will be the demodulated signal. In this code, I plot the demodulated signal, and you can see it here. Note that the demodulated signal nicely corresponds to the modulating signal. Last, let's take a look at the spectra of our signals. So here I will plot the absolute value of the spectrum of the modulating signal. That is what you can see here. And here I'm plotting the absolute value of the spectrum of my modulated signal. And that is here. Note that the bandwidth occupied by the frequency modulated signal is much wider than the bandwidth that we had with the amplitude modulation. The frequency modulation is less spectrally efficient. So this is how you can do the frequency modulation and demodulation in Matlab. In this example, we will take a look at the quadrature amplitude modulation. As the first step, we will again generate our modulating signals, but this time we will have two modulating signals, the inline and the quadrature component. The inline component will again be the chirp signal that starts at 1 kHz and finishes at 19 kHz. The quadrature signal will also be a chirp signal but with a decreasing frequency. It will start at 19 kHz and it will finish at 1 kHz. Both these signals are plotted here. The inline component is the blue line and the quadrature component is the red line. Now here I will start with the modulation. First I will set my carrier frequency to be 100 kHz, and on this line I will perform the modulation itself using the formula from the lecture. In this code I plot the signals. With this command I plot the inline component, here I plot the quadrature component, and here I plot the modulated signal. The results are here. These are the inline and quadrature modulating components, and this is the modulated signal. Now let's take a look at the demodulation. I will show you two approaches. The first one will be based on the analytic signal, and the second one will use some multiplication with cosines and sines and some low-pass filtering. In this first approach, you just apply the function Hilbert to your modulated signal, and that will give you your analytic signal. Then you frequency shift your analytic signal by multiplying it by this exponential. How this works was explained in the lecture. Next, to get the demodulated in-phase component, you just take the real part of your frequency shifted analytic signal. And to get your demodulated quadrature component, you just take the imaginary part of your frequency-shifted analytic signal. These two demodulated components are plotted with these two commands, and the results are shown here. You can see that the demodulated in-phase component nicely corresponds to the original in-phase component, and the demodulated quadrature component also nicely corresponds to the original quadrature component. Now let's take a look to the second approach to the demodulation. I will use the formulas that I explained in the lecture. First, I will take my modulated signal and I will multiply it by 2 times the cosine at the carrier frequency. Also, I will take my modulated signal and I will multiply it by -2 times sine at the carrier frequency. As I explained in the lecture, the resulting signals will contain the in-phase and quadrature component, but next to those demodulated signals, they will also contain some undesired high-frequency components. To get rid of those undesired high-frequency components, we need to design and apply a low-pass filter. In the previous exercise, I showed you how to design filters using the Matlab filter design tool, but here, for the sake of simplicity, I am just doing it with Matlab functions. To do it with Matlab functions, you first need to specify your filter. This is the upper frequency of your passband, this is the bottom frequency of your stopband, this is the allowed ripple in the passband, and this is required suppression in the stopband. This upper passband frequency of 20 kHz was chosen because we need to pass signals that go to 19 kHz. So when the filter passes the signals all the way to 20 kHz, it should nicely pass our demodulated signals. Now, this bottom frequency of the stopband was chosen with respect to those undesired high-frequency components that we want to suppress. Recall from the lecture that after this multiplication, the spectrum of this signal will look like this. At low frequencies, here you will have your demodulated signals, this is the carrier frequency, and somewhere around twice the carrier frequency you will have those undesired high frequency components. These are the high frequency components that we want to suppress, so if we set the bottom of the stopband of our filter to the carrier frequency, the filter should suppress these high frequency components nicely. And that is what I have done here. The carrier frequency is 100 kHz and the bottom of the stopband I have set to 100 kHz as well. This division by the sampling frequency and multiplication by 2 is just a scaling that the Matlab requires for these design functions to work. About these design functions, these two functions design an IIR filter with the Chebyshev approximation. This first function will accept the specification of the filter, these variables, and it will give us 2 parameters of the filter, the order of the filter and something that is called the Chebyshev natural frequency. Then you will take these 2 parameters and the ripple in the passband and you will input it into this function, which will give you the feed forward and the feedback coefficients of the filter. Once you have your coefficients, you can just apply the filter with these coefficients to your signals, that is, to these signals. The results are demodulated in-phase component and the demodulated quadrature component. In this code, I plot the demodulated signals. This part plots the demodulated signal obtained from the analytic signal, that is what you can see here and I have already commented on. This part plots these demodulated signals, which you can see here. These demodulated signals quite nicely correspond to the original modulating signals, but there are some deviations. Firstly, here you can see that it takes some time for the filters to start to work. In this transient, the filters are still adjusting to the input signal, and only somewhere in this time they start to give us the proper outputs. Also note that there is some time delay between the original modulating signals and the demodulated signals. This time delay is caused by these filters because they cannot work in 0 time. Now, I would note that this approach is often used for the real-time implementation of the demodulation. This approach, based on the analytic signal, could be implemented in real time, but not with the implementation that is used in Matlab. This function Hilbert first needs to have the entire signal measured, and only then it will give you the analytic signal. In contrast, this multiplication and this filtering you can recompute for each new sample of the modulated signal. So for each new sample of the modulated signal, you will get new samples of the demodulated signals. Now let's take a look at the spectra of our signals. Here I plot the absolute value of the spectrum of the inline component. Here I plot the absolute value of the spectrum of the quadrature component. And here I plot the absolute value of the spectrum of the modulated signal. The results are shown here. This is the spectrum of the in-phase component, this is the spectrum of the quadrature component, and this is the spectrum of the modulated signal. Note that in comparison with the spectrum of the amplitude modulation, the quadrature amplitude modulation takes the same bandwidth, but this time in the same bandwidth we are transmitting two signals, the in-phase and the quadrature component. Also, there is no peak in the middle of this frequency band. So if we transmitted this signal, we would not be wasting so much energy. So this is how you can do the quadrature amplitude modulation and demodulation in Matlab.